Hi folks. To continue with the previous lab, what we are doing today is I'm extending it to spanning tree lab number 2. So in this lab, what we are going to talk is we are going to talk about the standards 802.1d, which is the IEEE standard, and the Cisco proprietary, which we call PVST. So when we are using a spanning tree, as I said earlier, so if you look at a switch, if we are using redundant links, so we have more switches or we have redundant links. So what happens there is because the states of these interfaces or the ports, they are either forwarding or they are blocking or they are discarding. And then this is by way of these algorithms, A2.1D and spanning tree, we want to see how it works. Because without any spanning tree standard, the switches may go in a loop, and once they are going in a loop, they are wasting the resources, and there is a lot of broadcast and nothing is coming out. So to control that, this is what we do. Because traditionally, the main function of a switch is to listen, learn, listen, and forward. And then number 2, once it picks up the frames, once it listens, then it enters into its MAC address table. And then whenever any packet frame comes in, is going to go and do the unicast to that destination. Otherwise, if it doesn't know anything in the MAC address table, it is going to go send a broadcast. And number 3, the main function is also that how do we go and control the loops. So again, 3 things: forwarding, filtering. First one is it is going to learn. Number 2, after learning, is going to go and forward, or depending upon block. And number 3 is how to avoid the loops. So what we are looking at is how to avoid the loops and what are the rules or the standards which we use in switching. So the first standard was is by IEEE, which is the international standard. So Institute of Electrical and Electronics Engineers. So what they've done is they've made a rule 802.1d. Now when the Cisco implements this one, Cisco calls it a PVST. So the difference between these two is, main difference here is that the A2.1D means there is only one instance of a spanning tree per network. So it doesn't matter how many VLANs you have, system is going to go and use one spanning tree and all that. Whereas the Cisco figures out that no, because we may be using more than one VLAN in our network, so they are using the same algorithm but per VLAN. So that means if you are running VLAN 1 and VLAN 2 or VLAN 3, so each VLAN will have its own way of configuring the root port or the blocking concept or discarding concept or forwarding concept. But the default is when we see on Cisco, because we are sitting on a Cisco switch, so the default is PVST. Although when we run a command, show spanning tree, system does show you IEEE. And let me show you. For example, I am on this switch. When I expand it and I go to see a command line, and what I do is when I run a command, show spanning tree, so you can see that right on the top, system says spanning tree enable protocol IEEE. So what this IEEE basically means 802.1d. But when we go and run a command show run, that means we want to see what is in the RAM. So right there, system says spanning tree mode PVST with the spanning tree extended system ID. I'll talk about this one. So this clearly means that when we are running this spanning tree algorithm, so this is enabled by default on every switch. Now what it does, so it has 2 things be done. So for example, I have these 3 switches and I have connected them on different interfaces. So what is happening here is these ports, from where they are going to send it and receive it, system is deciding on which one is going to be in a forwarding state and which one is going to be in a blocking state. So to figure out all this, the first thing is system has to pick up one of these switches as a root bridge. And the root bridge concept is that system is going to pick up a root bridge based on the bridge ID. And a bridge ID means in a Cisco, 4-bit priority plus 12 for the system ID. So that means by default, whichever priority is smaller, system is going to go and make it a root bridge. Now, traditionally, by default, system is putting the same priority on every switch. So that means their system is not going to go and pick up a root bridge based on the priority. So what they do, they pick up with the MAC address. So that's why on the right-hand side, I have written the 3 MAC addresses of switch 1, switch 2, switch 3. I will show you that. And whichever is the smaller one, that becomes the root bridge. So if you can see that, one other switch, which is in this case, switch number 2, its MAC address is smaller than the others. So this switch becomes the root bridge. So S2 becomes the root bridge. So that means this bridge is the root bridge. So for example, let's go and check it. When you open the switch 2 and we go run the the same command, show spanning tree. So if you look on the top, spanning tree enabled protocol is IEEE. That means the same standard, PVST or A2.1D, as I said earlier. It is priority is 32,769. So this is based on the rule 32,768. That's the average, and plus in a PVST or in Cisco, they are adding +1 because of the VLAN. This is in VLAN 1. So that is called a system ID extension 1. So that means basically the bridge ID is equal to the priority plus the system ID extension. That means the VLAN. So for example, if I am in a VLAN 10, so this bridge ID will be 32,768 plus 10. So these machines are by default are using 4-digit numbers for the VLAN. So basically we can, I can show you this one. When I say show VLAN, so you can see that by default they are going to go up to 1005. So these 1002 to 1005 is not used because system is using it. So remaining all other ports are being used. So that means starting from 1, it keeps going up to 1001. Unless we go and make it extended, they can go for 4096. So once the bridge has become a root bridge, so every port on the root bridge is in a forwarding state. And when we say it is in a forwarding state, what is the role? The role we call it is designated. So you can see there on the screen, when the state is a forwarding, it is designated to forward, receive, forward, receive, forward. And then the remaining 2 other switches in this case, or generally you call it non-root bridges, what they do is they have to go and first, they have to decide which one, how they are going to talk to the root bridge with the lowest cost. Remember, lowest cost. Now, lowest cost basically depends upon your topology. So what are those costs? If you are using 100 megabits per second, or that is 19. If you are using 1 gigabits per second, its cost is 4. And if you are using 10 gigs, its cost is 2. So the smaller the cost, the better the performance. So because I'm using a fast Ethernet, so this cost will be 19. So this root bridge, what it does, it is sending the BPDUs, or you can say the broadcast. It sends it and say, well, to reach to my machine, my cost is 0 because this is the initial point. And then when this guy, switch 1 and switch 2, they are getting those BPDUs and they compare it with their own interface. Because this interface, as I said, fast Ethernet, cost is 19, this cost is 19. So then both of them are going to fix which one is going to be root port, because they are going to go and talk to the root bridge on this path. This is going to talk to this path or this path. So how do they decide? Number 2, the root bridge. So there's the algorithm. That means number 1, they decide on the cost. lowest cost. But here you can see that both of them are having same cost. This is 4, this is 4. Because this is fast Ethernet, this is fast Ethernet. This is a 0, it adds its own, 0 plus 4 is 4. It adds its own, 0 plus 4 is 4. So the cost is same. So when the cost is same, there's a tie. So then how do they break the tie? Then they look at the bit, the bridge ID. So this means system is going to go and after looking at the bridge ID, the bridge ID, remember I told you, 3268 plus the VLAN number. And then system is going to go and compare the MAC addresses, always. So whichever is going to be smaller, system is going to go and use that as root bridge in case there is a tie. So this becomes here on this switch, root port. So you can see on S1 here, root port is going to be forwarding, its cost is 19. This. And then switch number 3, this is going to say, well, I'm going to go and talk on this port. Cost is 19 to this one. So you can see the F3 here, and F3 is in a root port. So forwarding state is 19. So you can see that all those switches which are not root bridges, non-root bridges switches, they must have a path to talk to the root bridge. So that link is known as a root port. So every switch will have one and only one root port so that it can talk to the root bridge. This is the path concept. So this is done, this is done. So you can see that the states of all these ports, it is designated over a root port if they are in a forwarding state. Next, now once they have decided, now they have to go and decide on each segment because you have link here, you have link here, you have link here. Then system is going to go and see how they are going to go and have access on this link. So make sure that what we call it these ports as a designated port. This is called a root port. So every segment must have a designated port so that it can send the messages to the clients, the users, and everything. That means those devices. So now there is a designated port here, so they don't have any problem. They have a designated port here, they don't have any problem. But look into this part. So this side, they have to figure out that among these two, one of them has to go in a blocking state. Because if they don't block, then there's a flood. That means those loop things. So the next one is system is going to go and pick up which one is going to go and be in a blocking state. So you can see that system picks up this one, which is on switch 1. Again, we go back to switch 1, and you can see blocking state, although its cost is 19. But if you look into that system and compare this port, this number, and this number, and then system is going to go and decide on that. So this is 00B, this is BE22 and all that. And then system is going to compare and make it as a blocking state, and this becomes a designated port. So let's try to figure out now. So when a message comes from anywhere, let's say you have a computer here on this side. So when it sends it, if it is for this side, its system is going to go do the sending this way. And then this will come up to here, but it won't be, the frame won't be able to go to this side. It is blocked. Or if you are sending from here, system is going to send on this way, computers are going to pick up. If you have computers there on network, you have computers on this side, you have computers on this side, devices, or this side, the message can go there. But this is the blocking. So what is the rule now again? Simple rule is that if you are having a redundant paths in switches, you make sure that you have to have some kind of algorithm where you are going to go and block the frame so that the frames are not going to go and mess up this. Reason is because if it is free for all, so every machine is receiving that information. Every computer is having a duplicate or even triplicate copy of the same frame. And then they have to go and update their MAC address tables, which we call flapping. So it is going to be very inconsistent. So that is why they use this rule. Now, So once you have decided, you can see that once the system has decided that this is going to be in a forwarding state, this is going to be in a forwarding state. So you have to know that when we say we are having a role, which is our designated port, so designated ports are forwarding states. Then the blocking and alternate, the question about blocking and alternate is that this port goes in an alternate state, that this one is blocking. But in case something goes wrong with this, right, that means something goes wrong on this port, then immediately system is going to recalculate and it will start accessing this through this side. That's why they call it alternate. So let's check the tables. I want to show you a few things here. I will pick up on each one and I want to explain a few things here. So if I am on a switch which is how do I know which one is what? So you simply go say show spanning tree, and you don't have to type the complete. And let's read this one. So let's read from the top because this is how we have to know and we have to understand for the exam point of view. So number one is right now this switch, this instance is in a VLAN 1. Remember I told you VLAN 1 is a 4-digit number. So you can say 001. Or you can say, if you can say, well, it is 2, 3, 4. And remember I told you, if you don't have an extended format, we can go up to 1001 VLANs. So this is by default VLAN 1. We didn't do anything. So it has to exist because all the traffic is moving in VLAN 1. If you have only one computer, if you have one switch and you are not connecting with any of the switch, you don't care. But the moment you go and connect more than one switch, redundancy, more than one path in a switching, we call it a trunk port. That means they have to send the information from one switch to another switch and through different ports which we are connecting those switches with. Okay, so first thing is you have to make sure spanning tree enabled protocol is IEEE. IEEE is the international standard. The same thing is in Cisco, we call it a PVST. Difference, in IEEE, they say one instance of a spanning tree per machine, per switch. Whereas a PFT says, well, it depends how many VLANs you create. For every VLAN, they will be running an instance of a spanning tree. So in one, you may be a root bridge, and then in the other VLAN, in the other spanning tree instance, you may not, that switch may not be a root bridge. That is the idea of PVST. Okay, so per VLAN, only in Cisco proprietary. But in international standard, 82.1D, one instance of spanning tree per switch. Okay, the next thing we have to see, how do the computers, these switches know that which one is root bridge and which port is going to go where by default. So first thing is, if you look at that root, as I said, every switch will have a priority. Basically, it all depends on the priority, and that priority is a 32768 by default. Because bridge ID contains two parts, priority and system ID. This 4-bit plus 12-bit. So this 4-bit is from where we are getting this number. This is a multiple of 2, but you are seeing odd number 9. The reason is because they always add a system ID. That means which you are in whichever VLAN. So for example, we are in VLAN 1. So that's why 32768 plus 1 becomes this. Then this is the address of your switch. So this guy is going to send this physical address and say, I am a root bridge. So this bridge is root. And now you can see that system has picked up this as a root. That's why you can see bridge ID priority is this and this address is same. So in exam, when they say which one is the root bridge, you run this command and compare these two MAC addresses. You can see this MAC address and this MAC address same. So that means this is a root bridge. That's number one. Number two, you go check the role and the states. All the roles on a root bridge are designated port. That means they are in a forwarding state. Cost 19, as I said earlier, 19 because I'm using a fast Ethernet. The cost by default is 19, 19, 19. This is local thing. This is a local priority of a port. So every port, individual port has a priority. That has nothing to do with this priority. And this is point to point because I'm connecting my cable with point to point. One end here, the other end there. And then when we go to the other switch, whichever you go, and when you open it, you go this, and then make sure if interface is down or interface is disabled or you didn't have a cable, you didn't connect with the cable. We are not talking about that. The system calls it a disabled things. So we are not talking about those disabled interfaces, okay? We are only talking about those interfaces which are active. That means you are running a cable, they are on, they are up, they are sending information, they are receiving information, and they are receiving and sending through what we call a BPDUs. So to start these switches when they are under decision, every switch sends the BPDUs to tell the other that that switch is a root bridge. But once they compare as I said earlier, once they compare the MAC addresses, so whichever has the lowest MAC address becomes the root bridge, and then the others will not send the BPDUs again. They will be only getting those BPUs from their master, which is the root bridge. Okay, and now let's check on this one. We know that this is a show spanning tree. So you can see now the BPDUs tell this switch that the switch which is a root bridge is having this as a MAC address and your MAC address this. So clearly they will back off before it decides to become a root because this MAC is bigger than this one. You can see there. And then if you look at this second one, the next thing is on this interface, the root port is this, which is F03. So this is F03 is going to go, this is the shortest path or the lowest cost to go to the root bridge to talk to that. And then on the other side, because you need a designated port on each segment, so on this segment, this is being designated to forward. This one is port number 02, and you can see it can forward there. Now, question here is, if you look into this timing, this is very important. So this switch is getting this information through the BPDUs. So the cost is 19. You can see this is the root bridge. Which one was the root bridge? All designated ports with the MAC address of CAE. So when the message comes, that route sends the cost 0, but because it picks up on F03 on this port, so it knows that its cost is 19, so 19 plus 0 becomes 19. That's why this is the cost to reach to that. Now let's go to the third one, and then we just go and say show spanning tree. Again, you can see from the top, VLAN 1, IEEE is the 82.1D, the spanning tree algorithm. The root bridge MAC address is this. To reach to that, the cost is 19 because the root bridge always sends this cost 0. And then here, they are going to go and add 19 or whatever the cost depending upon that interface, outgoing interface. And so 0 plus 19. So this is 19A, this is 19A, and then system is going to pick up. This is a root bridge because there's only one path here. Okay, so it doesn't have to worry about that. Similarly here, they are only one path. So this becomes root port. The last part here is now, you can see this one now. On this segment, it has to decide what to do with this one. It is going to be designated port or is going to go in blocking. So as I said earlier, on one segment, you just need one designated. So this one system is going to compare these two. Whichever number is smaller, that is going to go and become the designated port. So you can compare areas. The competition was between S1 and S3. So S1 and S3, if you see, S1 is this, and S3 is this, 001 and all that. So because 001 is smaller than 00B, because B is 12 in hexadecimal, in decimal when you convert. So that's why this becomes on your, this goes in a blocking state. System is going to compare that. And then once it goes into B is a bigger one, it goes into blocking, and that is this. So that means this is going to block here. Now, so now there's no more looping, because the message comes here. If it is for this segment, they will deliver it here. If it is this segment, one of these guys can deliver it here. If it is on this one, this port can deliver it here. But this port is only listening there. It is just there for blocking. But it does pick up the BPDUs. So now only the root bridge is going to send the bridge protocol units information, which contains the timing and other things. And all others are going to go and just update those. Now, another very important point before we finish for today. So you can see when it says show spanning tree, the important point here is in a 2.1D algorithm, this timing. So you can see they say hello time after every 2 seconds. That means they are expecting that the root bridge is going to go and update them after every 2 seconds. That's number one. Number two, if something goes wrong with the root bridge and it won't be able to update those after every 2 seconds, so they have to wait. The other switches have to wait 2 times 10. That means this is the algorithm. 2 seconds times 10 means 20 seconds. So the other guys are going to go and wait for up to 20 seconds. And then they will, they are going to go and reconfigure who's going to become the root bridge and whatever, everything else. But before the final thing happens, that means before your network becomes active, there is another very important point is which we call a forward delay, 15 seconds. Because what the switches are going to do is they are going to go and learn. System is going to move into learn. And then from learning is going to go move into listening. So this forward delay from listening and learning each takes 15 seconds. So 15 times 2 makes 30 seconds. So that made 20 seconds. 20 plus 30 makes 50 seconds. So that means before they decide on a new Trump, you can see there, that means they have to take 50 seconds. Oh, well, this is what the Cisco says. This is very important. But if things are moving perfectly, after every 2 seconds, the root bridge is going to go and keep them updated. Okay. Now, question is, can we make another machine as a root bridge? Sure, we can do it, but that's not a part of today's lecture or video. What we are going to do is, at next lecture or next video, I'm going to show you how do we change the priority. If we want to make a switch, a root bridge, because traditionally in your real life in networking, the normal switches where we are working on these, like these Catalyst 2960, they are, we call them at access level, access point, access level, okay? Because most of the client's computers are connected with these switches. And the root bridges, maybe we are going to connect like 4 floors, all 4 floors have switches, and then we are connecting all of those. Then we need another higher layer switches, maybe 36, 560. So that means then all of these are going to be connected there. And so first is access layer and then the distribution layer. So the higher layer. So what we do is we may put, we may make one of those switches which are on our floor building or on building of floor number 4, the root bridge. Then how do we make changes? Because remember, in a network, like in every network, there has to be one root bridge. So by default, these rules which I showed you, but if we want to do it manually, if we decide, because in a networking, we may figure out that this is not working properly, if this is not very efficient. So then what we can do is we can make whatever as admin, we can go make whichever you decide to make it a bridge or the root bridge, okay? So hopefully you enjoyed the lecture. Keep working on these labs and lectures, and then see you next time, and take care.